All right, hi physics class. This is Mr. Mellinger with another lesson. Today is Tuesday, April the 21st, and we're still in the pre-grading period of distance learning that will start next Monday. This lesson, however, will be part of that, and this is a chance to do it early and get some extra credit for it. So this lesson will be on energy. Let's go ahead and talk about that. So in the video you saw yesterday, they mentioned there's three types of potential energy. And the one they really emphasized was elastic, and that's basically like a spring or a rubber band. Those things have elastic. If you pull on a rubber band or pull on a spring and then let it go, it will snap back to its original position. So while you were holding it, it had potential energy that turned into kinetic energy. A second type they mentioned was chemical potential energy. The simple example of that would be a battery. It has two different chemicals in it, and one of them pulls electrons away from the other, which is what electricity is. It's the movement of electrons. You usually deal with that in chemistry. We won't be dealing with that in this class, or maybe just a brief discussion later on. The third is gravitational potential energy, and that is very simple. If you pick up your pencil and hold it up above the ground, it has potential energy. If you then release your pencil, it falls and then it turns into kinetic energy, which is the energy of motion. So we're going to talk about those two today. So first, so on slide 39, gravitational potential energy is the force of an object due to gravity. And the formula for gravitational PE is mgh. So m is the mass, g is the gravitational acceleration, and h is the height. So mgh. Of course, mass is measured in kilograms. G is an acceleration. It's meters per second squared. And h is a height. Well, think about what a height is. It's really a distance. It's a distance that you are above the ground. So height is measured in the usual things that we would measure distance, such as meters. Now, for kinetic energy, the formula is kinetic energy is 1/2 the mass times the velocity that the object's going at exactly the moment you want to know the kinetic energy. That's instantaneous velocity. And then you square that. It seems like a tricky equation, but it's not. And we're not going to do a lot of equations here, although we'll run a few examples of these later in the week. So you have potential energy and kinetic energy. Okay, what is total energy? So total energy is simply adding the two together. Total energy is the sum of the potential energy and the kinetic energy. So TE, total energy, equals KE, kinetic energy, plus PE, potential energy. So if you were holding a pencil above the ground and you calculated using mgh that it has 60 joules of potential energy, and since you're holding it, it's not moving, so it has no kinetic energy, then that means the total energy in that pen would be 0 plus 60, or 60 joules. The law of conservation of energy states that the total energy of a falling object does not change. So as you drop that pencil, its total energy will not change until it hits the ground. Once it hits the ground, it releases the energy. Some of it is released in the form of sound. You hear a sound when it hits the floor. Some of it is released in the form of the pencil bouncing around a little bit. That would be putting the kinetic energy into the floor and back into the pencil again. So there's different ways it can be released. So as the pen is falling, the total energy does not change. So Ke plus Pe is constant. It stays the same. Okay, so let's look at an example here. Let's that uses these principles. You won't need K equals 1/2 mv squared, but the other two principles you'll need here. So let's say you have a 3-kilogram ball, and it's held 4 meters above the ground, and then dropped. So fill in the blanks for the energy as the ball of the ball as it falls. So if the ball is being held at the beginning, that means it has no kinetic energy. So all of the energy in it is potential energy. It's energy that could be converted into kinetic energy, but it has not done so yet. So the first thing we're going to figure out is the top left-hand line, and that's the potential energy at the beginning. And so the mass of the ball is 3. The gravitational acceleration is 9.8 meters per second squared, but we use 10 just to make the number simple. And the height is 4. So see how those numbers match up with the formula right above it, PE equals mgh. So if you multiply those, we get 120 joules of potential energy. Now, because it has no velocity, it means it has no kinetic energy at this point. You're still holding on to the ball. So kinetic energy, oops, I'm sorry. Okay. Actually, this is going to go down. So we're going to figure out all the potential energies first. All right, so 3 meters. So you see the formula. The only thing that changed was the height. The mass of the ball is the same, and the gravitational acceleration is the same. So you multiply those, and you get 90 joules. Okay, finally at 2 meters, or next at 2 meters, the only number again that changes is the height. So it's 3 times 10 times 2. That gives you 60 joules of potential energy. Notice as it's falling, the potential energy is getting smaller and smaller. At 1 meter, it's 3 times 10 times 1 as the height, and that gives you 30 joules. And finally, when it hits the ground, it has no height. It's really just before it hits the ground, 0 meters high. It has no height, so therefore it has no more potential energy. Okay, now let me go back to what I was about to say. Since it's not moving at the very beginning when you're holding it up 4 meters above the ground, that means it has no kinetic energy. So you put a 0 for KE because the ball is not moving yet. Now, based on the last slide, we know what the total energy is. I use E total here instead of TE. It's the same thing. And so it's 120 plus 0, potential energy plus kinetic energy equals 120 joules of total energy. Okay, now, what do we do next? Unless we want to, we can't figure out kinetic energy directly here because we don't know what the velocity is at any point while it's falling. We could figure it out, but it would take a lot of calculation, so we're going to skip that. So what else can we fill in? Well, remember what it said on the last slide, that as the ball drops, the total energy stays the same all the way to the ground. So we can fill in all of these lines right here. It's going to stay at 120 joules of total energy all the way until just before it hits the ground. Once it hits the ground, the energy is released. Now that we have that column filled in, we can go back and fill in the middle column because we know that PE plus KE equals total energy. So let's go ahead and do that. So 90 plus some unknown number equals 120. Well, you can just do that as a subtraction. 120 minus 90 equals 30. 120 minus 60 equals 60. 120 minus 30 equals 90. And finally, 120 minus 0 equals 120. So just take a look at this. As the ball fell, it had less and less potential energy because it had less and less height. But as it fell, its kinetic energy increased. Why? Because as an object falls, it speeds up, it accelerates, it gets faster and faster. And therefore, if you plug that velocity into the 1/2 mvi squared, you'll see that the kinetic energy is getting greater and greater as the ball falls. So this chart shows you the relationship between those things. Okay, so I have a brief assignment for you to do on this, and then we'll go on with another lesson tomorrow. Again, be in touch with me by email or over the phone. That's on the introductory sheet I sent out to you, and I'll help you if you have any questions. Okay, have a good day.